So the first thing that we want to do here is that I would probably want to put in some nodes just to make sure that we're all speaking the same language. And node analysis as well as mesh analysis help us in our thinking here. You can still go back to all those original type of thinking where you might say, well, we can see that this guy has to be what? Node VC. If you look at this node right here, you know that this is VL relative to the ground. And if I look at this node over here, we see that this guy has to be VS. And sometimes it's useful to place these to sort of like put you in the frame of what do I mean by current of a resistor? What do I mean by, you know, voltage across this resistor? Because these are what? These are nodes. They're potentials. They're not voltages. We have to take differences to get voltages. So the first thing that I always want to do when I'm going to start to get ready to solve for a circuit is I want to interpret what do I think is going to happen to the solution of this thing. We're solving for VC here. So if this source here, let's say turns on at t equal to 0, then that means here that I'm not going to get any voltage across the capacitor. As soon as that source turns on, it's going to have some transient behavior. So now, what I'm really interested in is looking at t equal to infinity. Because our differential equation, so our second order equation must satisfy VC of infinity like this. And I'll call that constant B. Right? It has to do that. So when I look at the circuit here, you can see as t goes to infinity, this guy goes to a short, and it kills off this whole branch. So immediately we see that B has to be 0. Right? The inductor kills off that whole branch. So when I go to look at my equation, I better have 0 terms on the right. I better get 0. If I don't get 0, there's a problem. Right? And then that's when I say, go back and figure it out. Okay? So now I know this, so now I'm going to go and do the steps. Right? So I'm going to do that same type of rhythm that I'm going after. I'm going to go after what? Steps 1.1, 1.2, and 1.3. All simultaneously. Then we pause to do the determinant of these guys here. So here we go. So I'm going to look at KCL. So when I look at KCL, I'm relating that current to this current. And you can see that they're in 2 different branches. So if they're in 2 different branches, the current of 1, not the source, the current of the 1 ohm resistor is what's feeding these 2 guys. So here we go. The current of the 1 ohm resistor must equal the current of the inductor plus the current of the capacitor. Then I keep moving. Replace the resistor values with either VC, IL, or VL, VC. So then if I do that, I'm going to look at this and I say, well, what do I know about this? I could write it in terms of VC, but that would be terrible because now you're going a whole loop all the way around. But clearly, look at the 2 nodes. So that means that the current of the inductor, of this resistor must be VS minus VL. So then I'm going to say VS minus VL divided by 1. I'll look at IL, that's in good terms. So this equals IL. And then I'll look at this guy, IC. I got to replace it with the capacitor equation. So I look at C. What's C? Is 1/2. Then it's the derivative of VC. But note, I did not change that IL here. So what I'm going to do now is that I'm going to take that IL and I'm going to bring it to the other side. As I bring it to the other side here, I'm going to get Vs. Now look at that VL. It's going to be by itself. So now I'm going to rewrite it so that it reads what? L is 1, so I'm going to get 1 times S hat IL plus 1 half S VC. Now I got it in all my terms right there. So now I'm going to go do KVL now. So now if I do KVL, you see that these two have to be related. And you can see that that branch is equal to that branch. So I'm going to sum those guys up now. So it's got to be what? So the way I'm going to do this here is I'm going to write VL equals the voltage across the 2 ohm plus the voltage across the capacitor. So you see that I got to deal with 2 terms here. I got to deal with that term, I got to deal with that term. Now notice, I've already written this equation once. I can't write it again. Because what I'm going to do here is that I'm going to get 2 variables equal to themselves. So when I do this, I'm going to convert this guy, but this guy, I have to do it a different way. And the way I do that here is I say, note that these 2 are in series, so they must have the same current. So then the current through the 2 ohm resistor must be IC. So here we go. So now I'm going to convert this guy. So I got 1 times S hat IL. And then on the other side, I'm going to write this as 2 IC plus VC. So in doing this, you can see I've got to go back and convert IC now. So if I do that, then I get what? S hat IL equals 2 times 1 half S hat VC plus VC. Okay, so I just wrote out those terms. So here's my second term right there. Oh my, this is one of those bad differential equations right here. So when you look at this, here's the problem right here. Remember, why do we identify x1 and x2, which I didn't even do here, right? Even I forget. Okay, we identify x1 and x2. Now look, what do we do with x2? x2 means that tells us about the initial condition. See how I have this guy right here? And see how this guy comes up right here? Which one's x2? You don't have that. So what do you got to do? You got to solve a 2x2 matrix. Exactly like the second problem in the quiz for chapter 7. This is exactly the same scenario here. We've set up 2 equations, and that's what we got to do. So it's a slippery thing. I can't do this. I can't define equation 2. Remember I said there's those 20% of the problems? This is one of them right now. So now, if you try to do this with the direct method, what do we say in Spanish? Ay chihuahua. It's a scorcher there. It's not a fun thing to do. So now what I'm going to do then is I'm going to set up the matrix now. So now I'm going to go to step 4. And now we want to derive the second order equation. So I'm going to set up my matrix. So what am I going to do here? I think I'll stick with IL as variable 1, and then I'm going to make VC variable 2, just like it says it up there. So here I go. So I'm going to write the first equation down. So it should be what? 1 plus S hat IL plus 1 half S hat VC equals VS. That's equation 1. This one here, I'm going to take the VC terms and I'm going to bring them to the other side. It doesn't really matter actually. I'm going to take this one to the other side. That might be better. So then I'm going to write minus S hat IL, and then I'm going to get 1 plus s hat VC equals 0. So now I'm going to matrix this guy. So if I draw a matrix for this guy, what does it look like? I'm going to go right down the column. So I'm going to get 1 plus s hat minus s hat, 1 half s hat, and then finally this term, which would be 1 plus s hat. And I get this right down. So now what I got to do here is that I'm going to do what? I'm going to take the determinant of the right side. So I'm going to come over here and I'm going to say, I'm going to solve for BC. So I only care about BC. So now what do? I'm going to take this column and I'm going to replace it with the BC column. Okay? So I got this derivative thing over here. So I take this guy and I replace it here. So then I'm going to get 1 plus s hat minus s hat, and then I get ds, then I get 0. So I got the determinant of that guy. So now I'm going to take the determinant. If I take the determinant, it's going to be this times 0, so I'm going to get 0. Minus minus, I get minus s hat with the plus sign times vs here. Now, if I have a constant source, okay, so if vs is equal to a constant, then that means then that this guy is going to be 0. If it wasn't a constant source, then I couldn't set that to 0. So now I'm going to focus on the d's here. And how do I focus on the d's? I'm going to take the determinant of this guy right here. Okay? So here we go. So now we're going to do d hat, bc. So now I go this times this. You see I'm going to get 1 plus s hat times 1 plus s hat. And then this times this. So I get a minus times a minus. So then I get a plus at the end, which will give me plus 1 half s hat squared, all operating on VC equals to 0. So now I'm going to do the algebra. So I'm going to get 1 times 1. I'm going to get 1 plus 2s hat plus s hat squared plus 1 half s hat. Then I'm going to collect my terms. So I'm going to get 3 halves s hat squared plus 2s hat plus 1 VC. So if we choose to convert this into derivatives, we can do this. I typically don't. Is there a difference between this and writing out the second order differential equation? No. I typically leave it like this. But if you choose to do this, then it would look like what? Look like this. And there's our second order equation. Now, let's check this thing. What we know here, in the limit, as t goes to infinity, for VC, it has to go to a constant. And we said that that constant had to go to 0. Well, here's what we will do then. We will take that constant and we plug it back into our equation. And you'll see here, if I take a derivative of a constant, clearly I'm going to get what? 0. My second term is, of course, 0. And then I get b equals 0. And check that out. It's exactly what we expected. VC at infinity, which we labeled as B, is 0. And that's what that differential equation tells me. Okay, that is step 1. Okay, that's step 1. So let's go to step 2 now.